As I said, I'm assuming that you know some quantum theory already. Nevertheless, I will start with a brief review of quantum theory, some aspects that will be particularly important and that maybe were not so prominent in your quantum mechanics class. It starts very simple. A quantum system is described in, and let me start, it's starting right now. Quantum system is described in. Many answers went in that direction. A quantum system is described in complex Hilbert space. In that complex Hilbert space, a pure state is represented by that also looked pretty good so far, what I've seen. Some people said a cat, a unit vector. Also, a density matrix is also correct, where, however, the pure state is a special case of that. The answer that I had in mind, but many answers went in that direction, is a unit vector defined up to an undetermined phase factor. Oh yeah, and then there are bra and cat vectors, and some of you mentioned that also. Now we move on. Not all states are pure. Some states are mixed. So a general state, which might also be mixed, is represented by okay. Now here, this is a point where maybe not all of you are so so clear in your answer. What I was hoping for was the density matrix or the statistical operator. These are synonyms. Some of you wrote a superposition of states, but that is not correct. Superposition is different from a density matrix. Let me show this to you. So if you have two pure states, say psi and chi, then a superposition of these two states would be something like alpha psi plus beta chi. So this is again a vector in Hilbert space where you have the normalization condition that the alpha squared plus beta squared absolute values must be equal to 1. This is a superposition. So here, this is a pure state. Psi is pure. Chi is pure. And the superposition, the linear combination of the two, is again a pure state. It's again a unit vector in Hilbert space, so it's again a pure state. A density matrix or a statistical operator is something else. A density matrix or statistical operator is denoted by rho. It's an operator typically denoted by rho. And it describes the situation where, for example, you have a container, and in that container are spins. And some spins are pointing up. So each individual spin is in a pure state. Yeah. And that would be described by a unit vector, spin up. And then you have other spins that are pointing down. So each individual spin, once again, is in a pure state. described by a cat spin down. And now you randomly, you have a source, say, and inside are these spins. And now the source randomly emits a spin. And you don't know if it's a spin up or a spin down. So with 50% probability, it's a spin up. And with 50% probability, it's spin down. How do you describe that situation? If, for example, you want to calculate the expectation value of some observable, A, right? Expectation value. In this situation, then you would say, well, with probability 1/2, this is a spin up. And in that case, the expectation value would have this form. And with another probability 1/2, it's a spin down. Case, the expectation value would have this form. And since I don't know whether it's spin up or spin down, each can happen with probability 1/2, I must take the weighted average of the two. Now we can slightly rewrite that. We can say the first expression, we can write that as I can insert a complete basis. I can say this is spin up operator A, spin up, basis state I, spin up. And likewise, in the second expression, I can insert complete orthonormal basis. I can say this is spin down, A, I, spin down. I can rearrange this a little bit and can write this as sum over I. Now this comes to the front. We have I, spin up, A, I. And I do the same trick with the second expression. So we have sum over I, spin down, A, I. And when you look at this first expression here, we can consider between the basis vectors. This is a product of two operators. Yeah, this spin up cat, spin up bra, it's also called a dyad, is a projector onto the spin up state. So another way of writing it is a projector onto the spin up state, and then times the observable A. So we have the product of two operators, and then we take the diagonal matrix element of that in the basis state I. So we have I, that's a diagonal matrix element, and then we sum over all the i's. We sum over all the diagonal matrix elements. Now the sum over diagonal elements, that's the trace. So actually what we have here, that is the trace of the projector times A. And likewise, in the second expression, the sum is the trace of the projector onto the spin down times the observable A. So at the end of the day, we have for the expectation value the following form. We have 1/2 trace projector up A plus 1/2 trace projector down A. We can write this as a single trace over 1/2 projector up plus 1/2 projector down times A. And this expression here in the round bracket, that is the statistical operator. And you see here, the statistical operator is a linear combination of the individual states. However, it's not a superposition. Yeah? So it's not a superposition would be something like we write it here. We could imagine a superposition as 1 over square root of 2 spin up plus 1 over square root of 2 spin down. That would be a superposition of spin up and spin down, and would again be a unit vector in Hilbert space, and it would again be a pure state. But that is different from the statistical operator that we have here. The statistical operator is a linear combination of these projection operators. It's not a linear combination of vectors. And it's not a pure state. Yeah, it's different from a superposition. I don't know if all of you have already taken the statistical mechanics course. If you have, then you should have encountered the statistical operator in your statistical mechanics course. And if you're unfamiliar with that, then I would strongly recommend that you read up on this, because that's a concept that we are going to need later on, the statistical operator. The properties of the statistical operator, this row that I just showed you on the handwritten page, it's a Hermitian operator. It's positive semi-definite, so it has non-negative eigenvalues, and it has unit trace. So maybe I can add that here on the handwritten page for the properties of rho. So we said that rho is always Hermitian. That's the first one. The second one is it's positive semi-definite, so it means the eigenvalues of rho are non-negative, and that reflects the fact that the probabilities that you calculate with the statistical operator, they are always non-negative. And finally, if you have a measurement and the probabilities for different measurement outcomes must always add up to 1, and this is reflected in the property that the trace, so the sum of the diagonal elements of rho, is equal to 1. A pure state is a special case of a mixed state or a general state. So a pure state can also be described by a statistical operator. In that case, the statistical operator is a projector. One way to see that is when you calculate the expectation value of an observable in a pure state, then the expectation value, as we said before, is given by psi a psi. And with the trick that I showed you before, this can be written as the trace of psi psi a. Yeah, that's the same trick as before. You see here in the calculation up here, yeah, the final form is the expectation value of A is the trace of statistical operator times observable. When you compare that to the expression below for the expectation value in a pure state, you see that this psi psi, this dyad, takes the place of the statistical operator up here. So in this particular case, the statistical operator rho is psi psi, and that is a projector. A projector, quite generally, is an operator which has the characteristic property that its square is equal to the projector itself. And indeed, if you take psi psi and you take the square of that, so you apply it to psi psi once again, since this is a unit vector, this scalar product is equal to 1, so this is equal to psi psi. So it is a projector. And this holds generally that a statistical operator describes a pure state if and only if it is a projector. So that was the question, the quiz question I had about the statistical operator. Now let's move on. I know we are approaching the end of the session, so let's quickly go through this quiz. An observable is represented by, now it's your turn. But I'm sure you know this all. An observable is represented by a Hermitian operator, and the eigenvalues of that operator correspond to the possible. The eigenspaces associated with these eigenvalues, so this can be eigenvectors, or they can be, if the eigenvalue is degenerate, it can be an eigenspace. Then the eigenspaces, you can understand them, interpret them as the associated propositions or statements about the measurement outcome. Next, the expectation value. Well, we talked about that before. I showed you already the formulas for the expectation value of an observable. It can also be written in a slightly different form. And let me show you that. We said that, and let me work with the general case, that the expectation value of an observable is given by the trace of the statistical operator times the observable. We said that this is psi if it is a pure state, but I would like to continue with the general case of a statistical operator. We can write it in a somewhat different form using the fact that every observable A is described by a Hermitian operator, and every Hermitian operator has a spectral decomposition. And the spectral decomposition says that the operator can be written as a linear combination, and we always have sums because in quantum computing we always work in finite dimensional Hilbert spaces, so we never have integrals, we always have sums. That makes it a lot easier. It can always be written as a sum over eigenvalue AI times associated projector. Yeah, so this projector Pi projects onto the eigenspace associated with the eigenvalue AI. Yeah, so this is an eigenvalue, and this is a projector onto the eigenspace. And if we use that spectral decomposition and put it into the formula for the expectation value, then we get the form that's the sum of rho trace rho Pi times AI. So we have a linear combination of the eigenvalues, and the factor in front of the eigenvalue is the probability with which the eigenvalue is measured. So that's the probability of the eigenvalue AI in the state rho. Yeah, so another way of writing the expectation value of an observable is as the probability weighted average of the eigenvalues of that observable, and the probabilities are given by the trace of rho times the projector onto the eigenspace. Now this formula here for the probability of a measurement outcome. So that's the probability that when I perform a measurement in the state rho, I will measure the eigenvalue AI of this observable. And this formula here with the density matrix is known as Gleason's theorem. And this is a name that you may not have heard, but you are certainly know the a special case of that, namely when the state is pure. When the state is pure, then the probability of measuring the eigenvalue AI in this pure state psi. So let's say rho is the projector, say psi psi. We can use Gleason's theorem in the form above. So it's the trace of rho, but rho is now psi psi, times the projector onto the eigenspace associated with the eigenvalue. And then sort of using our previous result in reverse direction, we can write that trace as psi pi psi. And in the special case, further that the eigenvalue is non-degenerate. So if the eigenvalue is non-degenerate, that is, the eigenspace is one-dimensional, then the projector onto the eigenspace is simply the dyad II. Then the formula for the probability simplifies further, and this becomes psi I psi, which is the same as the scalar product of the eigenvector I with psi and then absolute value squared. And this is, I'm sure this is a formula that you have all seen in your quantum mechanics course. And as it turns out, it's a special case of Gleason's theorem. And this special case is known as the Born rule, after Max Born. So this is another element of quantum theory that I hope you know. And let me go through the remaining points, some of which I already covered. So in a pure state, probabilities are calculated with the Born rule. That's what I just showed you. And in a mixed state by means of Gleason's theorem. Then there are a few questions about observables and their measurability. I think this is pretty elementary, so I think I will do without the quiz here. Two observables are jointly measurable if and only if the associated operators commute. I'm sure you all know that. And in case they do not commute, then the respective measurement uncertainties obey an uncertainty relation. Now, when you measure a pure state, when you measure an observable, then after the measurement, the state in generally is different from the state before the measurement. The state generally changes. In the special case where you measure a non-degenerate eigenvalue of an observable, then you can be sure that after the measurement, the system will be in the associated eigenstate. So previously you had an arbitrary, say, superposition state, but when you measure a specific non-degenerate eigenvalue, then afterwards you know the system will be in the associated eigenstate. If the eigenvalue that you measure is degenerate, so you have an eigenspace, then there's not a unique eigenstate of that observable. What happens then? In that case, let me illustrate briefly what happens in that case. And let's pretend Hilbert space is a three-dimensional real space, so I can draw it. Yeah, so let's say we have a three-dimensional space, and you have an observable which has two eigenvalues. One of them is non-degenerate, the other one is degenerate, and it has a two-dimensional eigenspace. Let's say it's that plane here. Let's say this plane is the eigenspace, is an eigenspace of an observable A for the eigenvalue AI. Okay. And now let's assume that prior to measurements, you were in this state, psi. So what happens? What happens after the measurement? There are many eigenstates in that plane. So just saying that afterwards the system is in an eigenstate doesn't specify the state uniquely. It's a particular one in this plane. Exactly, it's the orthogonal projection of psi onto that plane. So previously I have psi, and then afterwards I project psi onto this plane, onto this eigenspace. Now the projection in general no longer has length 1, so I have to normalize it. So I have to divide by the norm of that vector to get another unit vector. But essentially, that's what happens. You project orthogonally onto that eigenspace. What happens to a statistical operator? Now, this is not so easy. That's usually not covered in the standard quantum mechanics course, but it's not very difficult either. Let me show you what happens to a statistical operator. And let me begin with the special case where the statistical operator actually describes a pure state. So rho is psi psi. We just discussed that upon measuring the eigenvalue AI, the unit vector psi, the state vector, is projected orthogonally onto the eigenspace. So what happens to the psi's? And that applies both to the ket and to the bra. So the first psi is projected onto the eigenspace, and so is the second psi. So basically, we have a projection from the left and from the right. And then once again, we have to make sure that the resulting statistical operator is normalized. Remember that, I mean, there are two ways to argue. One is we can say, in both cases, we divide, like here, by the norm of the projected vector. So we get it twice. So we get the norm squared. And that is nothing else but psi projector psi. That's the square of the norm. Okay. Which we can write again as the trace of psi psi pi. And on the numerator, we have still the same pi, psi, psi, pi. And now we write the projector onto psi as the statistical operator again. So this psi psi in the middle, that was our statistical operator. So that was pi rho pi. And in the denominator as well, we have trace rho pi. So effectively, what happens is that the statistical operator rho, after measurement of eigenvalue ai, becomes this expression here to the right. So we apply projectors from both sides to the statistical operator, and then we divide by the trace to ensure the normalization. And I showed you this formula for the special case of a pure state, but actually it holds for a general statistical operator, for a general density matrix. The proof of the general case is a bit trickier. It's you have to think a little bit more why this is so, but maybe by analogy you see that it is plausible that it has this form. And this rule for the update of the statistical operator after a measurement is known as Lüder's rule. So this is perhaps something which is really new to most of you. This is Lüder's rule. And I think we've already almost done it. The last question regards transformations, and these can be either time evolution or they can also be symmetry transformations. I rotate the system, for example. How are they described? Well, I'm sure you know these are described by unitary operators.